Hello, Calculus 30. Today we are looking at finding asymptotes and intercepts, and we're looking at page 21 in your notes. Now when we look at this, all of number 1, number 1 is all questions you've done before. We know that vertical asymptotes come from the zeros in the denominator, so we can easily find that out, and we factor. We get that, and we know the vertical asymptotes happen at x is equal to 5 and x is equal to -4. Horizontal asymptotes, we know to look at the degree of the numerator and the denominator. We see that the numerator, the degree is 1, and the denominator, the degree is 2. The rule that we use here is if the degree in the numerator is smaller than the degree in the denominator, then the horizontal asymptote will happen at y is equal to 0. Okay? So when we look at this question, then we know that the horizontal asymptotes happen at y is equal to 0 in this case. Okay, let's look at B quickly. Again, when we're finding vertical asymptotes, we look at the zeros in the denominator, and if you were to factor that, take out the common factor, you would find that there are vertical asymptotes at x equals 0 and x equals 2. Horizontal asymptotes, then, in this case, we look at the degree, and we see that the degree is equal. So we use this rule. Degree in the numerator is equal to the degree in the denominator, then the horizontal asymptote happens at y is equal to the ratio of the leading coefficients. Okay, and in this case we can see then that this is going to be at y is equal to 6 over 2, which we know is equal to y equals 3. Okay, and if you wanted then to find the limits, you could show this, the proof of this, the limits as you go from, if you wanted to find it, let's see, as x is approaching, you would do -infinity of the question, the function, and you would also find the limit as x approaches positive infinity, and you know if they're the same, then the limit exists. And when you do that here, you would solve it just like we did in Unit 4. You do find the value of 3 in this case. Okay, if we move a little bit lower here, I'll extend the page. Okay, we have this case then. If the degree of the numerator is greater than the degree of the denominator, so this is the new part. The degree of the numerator is greater than the degree in the denominator. So this is what we're learning new today. Then there might be an oblique, which means slanted line, or parabolic asymptotes, or there could be 2 horizontal asymptotes. And we're just going to go into 2 examples of finding these. We're not going to go into a lot of detail in this section. So let's move on to the second example. Okay? So you can turn over to page 22. When we see this, I was going to move this off. When we see this rational function and are looking for vertical and horizontal asymptotes, we can see right away there's vertical asymptotes at x is equal to -3. That's from the zeros of the denominator. Then for horizontal asymptotes, we look at the degrees and we see that the numerator is greater than the denominator. So somehow now we know we could come up with a parabolic asymptote or an oblique asymptote, or 2 horizontal asymptotes. The way we do that is, number one, by doing long division. So we want to simplify this rational expression. So we have x squared plus 6x being divided by x plus 3. And we do long division just like you learned back in grade, 4. We ask ourselves, what do we need to multiply here? Multiply this by in order to get x squared, while we multiply by x. And we keep the degrees of the x's in this line here. So x times x is x squared, x times 3 is positive 3x. We subtract that, and we'll get 0, and 6x minus 3x is positive 3x. Okay, now we don't have our constant term here. We can write in a 0, bring it down, and we ask ourselves, what do we multiply x by in order to get 3x? Well, positive 3. 3 times x, positive 3x. 3 times 3, positive 9. Subtract that, and we should get 0. And 0 minus 9 is negative 9. Okay, so that result tells us that our answer when we divide is x plus 3 with a remainder of 9. We write that as x plus 3 plus the remainder, negative 9 over x plus 3. Now we ask ourselves, or we look for the limit, what happens when x goes to positive infinity or x goes to negative infinity? And specifically, what happens here? Well, we see that as x goes towards positive and negative infinity, that this expression approaches 0 or gets infinitely small. So it's negligible. Therefore, we say as x approaches or goes towards positive or negative infinity, f of x approaches what's left. It approaches this line, or this oblique asymptote, of x plus 3. So we say then that our oblique asymptote, I suppose, is equal to y equals x plus 3. And as shown in this graph here, I think you can get a glimpse of it there. The red is the function, our rational function, and our oblique asymptote, you can see the expression here, is the blue. It gets infinitely close to it, but does not touch. Okay, let's flip over. Again, I was going to mention on page 249, there's a few more examples of this. One with an oblique asymptote is example 4, and parabolic asymptote is example 5. Okay, so looking at this next one, this is a parabolic asymptote, and we're again going to start with long division. I guess we should start with naming the vertical asymptote from looking at the zeros in the denominator. We've got a vertical asymptote at x equals negative 2. Okay, so let's do long division here. We're going to divide x cubed. Now don't forget the 0x squareds needs to be listed in there. Minus 4x plus 1 is being divided by x plus 2. Okay, what do we multiply x by in order to get x cubed? Well, positive x squared. We multiply x cubed, x squared plus or times 2 is 2x squared. We subtract that, and we should get 0. And 0x squared minus 2x squared is minus 2x squared. We bring down the negative 4x. What do we need to multiply x by in order to get negative 2x squared? Negative 2x. Multiply that through. Negative 2x multiplied by 2. Subtract that. And we get zeros all along. I'm going to write it in there just to be thorough. Okay, what do we need to multiply x by in order to get 0x? Well, 0. There'll be 0 constants here. 0 will be 0x plus 0. We subtract that, and we have 0, and 1 minus 0 will be a remainder of 1. Okay, so we know then, I'm going to move this vertical asymptote out of the way, we know then that f of x is equal to x squared minus 2x plus the remainder, which is 1 over our divisor. Okay. Now, as x approaches positive or negative infinity, we find that this remainder is negligible, very small, 0, and so we can say that as x approaches positive or negative infinity, f of x is going to approach or get infinitely close to x squared minus 2x. And so our parabolic asymptote, I don't know if that's the right symbol, maybe just write the word asymptote, would happen at y is equal to x squared minus 2x. And let me pull the graph up here. You can see the red, a very unique graph. You can't see it, it's touching so close to the asymptote here. The red graph goes down, and then there's a asymptote, which we know here at -2, and then the red, our function, is a parabola shape there. So our asymptote, that it gets infinitely close to and doesn't touch, is given by the blue graph, which is a parabola that squeaks in between and comes up. Okay. For those of you who are wanting to investigate these next examples, when we see functions with radical signs or with absolute values, that's the next two examples, we will probably see that we have two horizontal asymptotes, okay? So you go through it much the similar way. You can look at the example on page 250 to investigate that. I'll also say that in your assignment there won't be questions like this. If you're wanting to investigate it for your own self, you can go ahead. Okay, question 5 deals with an absolute value. Same idea. Mail it, please. So we won't go too in-depth in finding the x and y intercepts. This is a concept that you've practiced many times before. Y-intercepts occur when x equals 0. That makes sense. And I've done that here, put a 0 in for x. That evaluates to -2, which means that we have a y-intercept at x equals 0 and y equals -2. And that, of course, is right, that, of course, is right here on the y-axis. The x-intercepts are a little more tricky to find, usually. That occurs when y equals 0. So we put a 0 in for the f of x in this case, and we want to solve for x. Now, usually that involves factoring first. So you can see here in the numerator, that's a sum of cubes. Remember doing that? The cube root of x. Same sign. This is that SOAP principle. Cube root of the last term, x squared, opposite sign, 2 cube roots multiplied together, always positive, and square the last. All over. You can factor the denominator if you want. Now we will cross multiply, and the denominator will be multiplied by 0. So in fact, we don't need even to write the denominator. Okay, then we need to figure out the zeros. So from this first factor, x is going to be equal to -2, and the second factor, I'll tell you right now that we can put that into the quadratic equation, and it happens that there are no real roots. The discriminant is negative. So we will have this one x-intercept at -2, 0, which the graph, when I put it into Desmos right here, shows. Let's look at B, which is the exact same thing. You're going to find the y-intercept by putting a 0 in for x. You're going to find the x-intercepts by factoring this polynomial. You've done that before. You're going to need the first rule of the factor theorem as well as synthetic division. And you can see the answers. I'll leave you to do that on your own. Here's the y-intercept answer, and x-intercepts are given by those three. If you need help, text me.